All right, so I mentioned before that this is kind of, I like to call this the natural disaster chapter, and we're continuing with that theme here. That in the bottom corner there, that's a picture of Chernobyl. Chernobyl is a location in the, I believe it was in the old Soviet Union, which had a tremendous nuclear reactor meltdown. I believe it was 1986. And the problem with a nuclear meltdown is that the compounds, things like uranium or plutonium, they have what's called a half-life. A half-life is how long it takes for that compound to decay. Radioactive things tend to have enormously long half-lives. So, for example, if you had a dangerous substance like uranium with a half-life, in this case, of 4.47 billion years, that means if you had like 10 grams of it, 4.5 billion years later, there would still be 5 grams left. It takes an enormous amount of time for it to go away or dissipate. So Chernobyl is now off limits. No person is legally allowed to go there because, of course, they could get contaminated with radioactive waste. So it says in this problem, uranium-238 is a compound with that half-life for almost 4.5 billion years. And the following equation, this one right here, gives us equation for, and let me write a little bit bigger so you can see it. It gives us a way of telling how much substance is left. So what do each of these things mean? Y means the current amount of, in this case, uranium, or whatever compound you happen to be finding. You can do this with carbon-14 or any other chemical that you might have studied in chemistry or a science class. A stands for the original amount. Okay, A is the original amount. K is the rate of change, and the reason we have a negative right here, it's hard to see in this original, that's why I wrote it bigger, but we have a negative when it's a case of exponential decay, meaning that the curve, the graph is going to go down. If you were doing the same problem for exponential growth, like if it was something that was growing, let's say population, the equation would be this, it would be y equals AE to the positive KT instead of negative. And then T stands for the time in years. So we have two things that we have to do. First, we have to find K, which is the constant that shows the rate of decrease. And this formula is actually very similar to one that you'll see when we talk about continuous compound interest. The one for that, we use A for the amount of money, P is the original amount of money, and then it's called the PERT formula. But you can see it's very similar. P is like A right here. E is the same. E is the number. And I'll show you where to find that in the calculator. It's 2.718. And then R is the rate, just like K is right here, and T is still equal to time. So first of all, we have to find what K is. And here's the thing, they're not telling us, at least on part A, they're not telling us how much uranium we originally had. So when you don't know the original amount, you call the original amount 1, because 1 stands for 100%. So I'm going to put in 1 for A. E is still a number, and I'll show you how to find that in just a sec. We have negative K, and then T is going to stand for the time. Okay, and the time for a half-life is 4.47 billion. So that's 4,470,000,000, nothing thousand and nothing that number. So it's a huge number we'll have to put in. And then remember, Y is the current, or in this case the final amount. Well, we started with 100%, and this number tells us the half-life. It tells us how much time passes before it gets cut in half. So that means the final amount will be 0.5. It will be half of what we started with. So we basically have to solve this equation for E. And the way that we can do that, the way that we get, essentially we want this exponent to come down. In order to solve an exponential equation, we have to see what's being done and do the opposite. The opposite of raising something to a power is taking the log. And the question I have for you to think about is, what log would you want to take right here? And you could take any log, but the best log to take would be the natural log, the log with a base of E. So we have this right here still. Again, this massive number for almost 4.5 billion years, and then whatever I do to one side, I have to do the same to the other. So I'm going to take the natural log of 0.5. Okay, then what do we do with this? Well, remember, raising something, taking the natural log and then raising e to the power, those things are opposites. This is another way of saying, what do I have to raise e to get e raised to this power? And the answer is I have to raise it to that power. I have to raise it to negative 4.7. I'm just going to abbreviate this because we'll put it in the calculator in just a sec. That much times k equals whatever ln of 0.5 is. Okay, so let's actually put this in the calculator so we can solve that for k. And of course, what we're going to need to do is divide both sides by negative 4.47 billion. And then I'm going to show you how to store that value because we will use it in the very next example. So let's do that right now. All right, so by the way, if you're wondering where E is, you would hit the second button, and then E, it's a little bit hard to see on my screen, but it's right above the divide button, which just lit up in red. So let me click that again. So second E, and when you press enter, you can see it's 2.718. So we want to do the natural log ln of 0.5, and then we had to divide that by negative 4.47 billion. So negative 4 billion, you got to be careful with the zeros here, 470 million, 3 more zeros for the thousands, and then 3 more zeros for the last places. So we get this right here. So that's e to the negative 10 means times 10 to the negative 10. It's an incredibly small rate of decrease, and that makes sense because it takes 4.5 billion years for it to just decrease by 1/2. So here's how you can store that. You hit STO, and that just lit up in red on my screen. It's right above the on button. And then you hit alpha, which is kind of like caps lock in a calculator, and store that as, you can probably see there's a bunch of letters on most calculators. They're listed in green, and that's how you access them. You press alpha. I'm going to store it as alpha K, which is right above the parentheses. And why would you do that? Well, first of all, we're calling it K in our equation. That's what the rate of increase is. But now notice if I hit alpha K again and I press enter, that number, now the calculator, whenever it sees alpha K, it uses that number. So sometimes people ask, well, what if I don't want to use K to be that number anymore? You can just overwrite it. You can store, if I press 3 and then I do alpha K again, I store that as K. Now K will be 3. But for now, we'll store it like that so we can use it for the next part of the problem. So that's what K equals. Let's look at what the rest of it's asking. Okay, so the rest of it is saying if there was originally 10 milligrams of uranium, but now only 7 remain, how much time passed in between, in the interim? Okay, so here's how we can do that. We could say there were originally 10. So that means if we're using this equation, A is equal to 10 now. E is still the same. Negative K is that crazy number that we saw there, something times 10 to the negative 10. So obviously we're going to fill that in the calculator in just a sec. They're asking us how much time. So that means we don't know what T is. And we know that our final amount, our current amount, is equal to 7. So let's solve this, or let's get it in a position where we can solve it. We need to get rid of the 10 by dividing. So when we do that, we're going to have 7 over 10 is 0.7. And then again, I want you to think about this. How would you get the exponent to come down right there? And the answer is we're going to do the same thing we did on that prior equation, which is on the prior part of this equation, which is take the natural log of both sides. Those will cancel, and we're left with negative KT equals ln of 0.7. Okay, now we need to, and actually let's keep something in mind. This actually should work. We need to divide by negative K on both sides, and when we do that, we'll get our T value. So the natural log of 0.7 divided by negative K. Let's put that in the calculator. So we have ln of 0.7, and we will divide that by, it's decay, so we're going to divide it by negative alpha K. And remember that uranium takes a really long time to go away, so this should be a pretty large number if we did this correctly, and it is. You can see that looks like 2,300,142,083 years. That's how long it would take for just 3 milligrams of uranium to decay, and so you can probably tell why Chernobyl is off limits to all human beings, because only 2 billion years go by, and you've only got about 30% of it that's gone at that point.